from Professor Columban Hutter, and we'll start.
Thank you very much. I want to begin by saying thanks to IMA for inviting me for this conference. Here's the title of my talk. It's a little bit outside of the main activities here, but it fits well into it. We look at the brief laws, and these we have seen this week are either formulated as single constituent media or as multi-constituent media, and I'm concerned here with these. And the latter ones are formulated as mixtures of, say, the Trustellian type formulations and multi-phase systems, the most prominent representative of which is the School of the Chemical Engineering in Princeton. One says that mixtures and multi-phase systems are conceptually differently treated. They lead to different formulations, and this raises the question which one is better than the other, or how can we decide what the two approaches make them different. I want to do this in the context of these two pictures and deduce a model which does everything before the initiation of the destabilization of, say, a dam, so it handles the quasi-static behavior at equilibrium, describes the destabilization via localizations and shear band formations, does the catastrophic motion, and the deposit at rest. For this, my claim is a unique answer or a satisfactory answer is given by thermodynamics, and the big question is here, why? And all I want to give here is to tell you that what the difficulties are and how thermodynamics tries to resolve these. I'm not going to show any of the proofs. So again, we have the postulational mixture concepts, the multi-phase system concepts. They are different, and people of the representatives of this class claim they are better than that class, and vice versa. And I want to objectivize this. Basically, both approaches lead to balance laws or balance-like statements, but in these statements one has unspecified quantities, phenomenological quantities, which must be closed, and the claim of I'm better than you or you are better than I can only be made once these closure conditions have been given, not before. Let me explain this with the use of a two-phase model of fluid and the solid. Here are the balance laws of mass. Here are the balance laws of linear momentum for the solid and the fluid. On the left-hand side is cleared. On the right-hand side we have the mass production rate densities. Here on the right-hand side we have the pressure gradients, the extra stress tensors, the divergence of them, the interaction forces, and the gravity forces. And the variables are the densities, the velocities, the mass production rate densities, the pressures, the extra stresses, and interaction forces. And if you count these and account for the fact that we have a production sum relationship, the production rates sum up to 0, this implies in this case these two statements, then we come up with 26 variables. I use the notation with a nova bar for a physical quantity when I have a density per unit volume. I do not use a nova bar if it is per constituent volume.
The actual forces, they don't have to cancel out because they're at different points in space.
Which forces?
Well, the MF and the MS.
They have to cancel out as interaction forces.
Not if it's particles at different positions.
Well, let's wait and then and then we discuss. Well, in mixture theories, they have to cancel out. Let's take a simple case. in which the C's are 0, no chemical reactions or no abrasion or fragmentation. The ideal, we take the fluid ideal, the solid Newtonian, and the interaction force in this type. I call this type of closure a Darcy closure, so this is only for vocabulary, and this is static case, which we also have to close. So we are left with the pressures, and we are left with this, and these poses problems. In classical mixtures, the partial pressure is usually defined as a function, given as a function of the partial density, and if the material is compressible, and you write down, sorry I forgot this to say, the partial density with the O bar is the true density times the volume fraction. So if you do that, write it down in this way, then you get this relationship. If you have a density preserving fluid or solid, then this rho without a Nova bar is a given quantity, so it only becomes a function of the volume fraction. The result is that this is a statement about, a closure statement about configuration. This is a closure statement for fixed configuration about material properties, and so this kind of closure is not sufficient. So we better split it up in two, in which one describes the material property and the other describes the configurational property, and we call this the thermodynamic pressure, and this we call the configurational pressure, and the dot indicates that there may be additional variables, and the question mark says, is there anything else?
What do you mean by configuration?
I mean the geometry of the pore space in this case.
How does
Okay.
that do with pressure?
Sorry?
How is that associated with the pressure?
Yeah, you will see it.
Oh, we'll see. Oh.
So just be a bit patient. Okay? Because the volume fraction gives us an additional variable. We treat it as an internal variable and write down a balance law for it. And these two balance laws are the ones I write down for the fluid and for the solid. It essentially says in the global form that the time rate of change of the volume of the constituent is given by a production term, each one by the production term, and these do not have to add up to 0. Okay, if you add them up. So I hasten to also mention that Goodman-Cohen and Wilmansky have derived or presented different equations. These were used by us. By us, I mean Bob Svensson and I and some of our students. Saturation is another complexity that enters. I use the definition for saturation that the sum of the volume fractions add up to 1. This means the constituents fill the whole space, and since this is a constraint condition, we end up with a constraint pressure for it. I call it this is a sigma. I call it saturation pressure with sigma, and it says something about the sum of all saturation pressures in the material, in the mixture, but we need a saturation pressure for each of the constituents. So people usually do that in an ad hoc fashion. They say, well, the total saturation pressure distributes among the constituents according to the volume fraction. This is a conjecture. It's never proved or very seldom proved, and this postulate has been determined by some people as the assumption of pressure equilibrium. Okay? But this is not a necessity. The factors here could be anything that adds up overall constituents to 1, and two people who have not done it this way are Savage and Iverson, who wrote down an additional equation for the pore pressure. in this case. I say thermodynamics should, and I hope I can in my time demonstrate that it will fix the inconvenience. There is an additional difficulty, and here it really becomes messy, with interaction forces. The interaction forces for the solid or the fluid is here an equilibrium contribution, and the Darcy term, I have repeated it here. I make three question marks here. What is it? What is the equilibrium contribution? And there are non-unique presentations in the literature. If you look into the old civil engineering literature, you find here a 0. If you look into the geophysical literature, you find pressure times gradient of the volume fraction. What is right? Okay, that's the question. What is right? And this indeterminacy allows us really to do everything we want. Assume I have given this quantity, and assume moreover that that given quantity can be represented in this form. Then, since the interaction force and the stress divergence always appear together, I can throw this into the stress tensor and come up with new right-hand sides. For the momentum balance, the pressures remain the same. I get new stresses, and I get new interaction forces. The new stresses are shown down here and here. There are three crucial things I have to say about this. First, if this is really a divergence, they add up to 0 if you have assumed that those add up to 0. If this is not a divergence, but say a viscosity, a volume fraction times a divergence as it is done by Anderson and Jackson, then you can throw the divergence into the whole thing and get a different expression for MF1, and those MFs don't satisfy the summation. Maybe you are now satisfied that they don't need to sum over to 0. Okay, here I've expressed this in terms of the fluid, and now I come to the third point. If I look at the new stress, I have indices F here. Both are fluids, so I say the fluid stress becomes a fluid stress. But the solid stress for this splitting becomes a difference of a solid and a fluid stress. I don't know, and I cannot say anymore, at least emotionally, I cannot say that this is a solid stress. Had I written this for S instead for F because of the sum relation, then I would have an S at this place and an S at this place, and I would reverse everything. I could say, well, this new stress is a solid stress, and I don't have a new stress which is no longer the fluid stress. Conclusion, this is a mess. Okay? We can't believe anything for sure. So we need thermodynamics, and we have done thermodynamics with the entropy principle by Inge Müller. I'm not going through the details. We need all balance laws for this: mass, momentum, angular momentum, energy, and here's the entropy inequality. And we need the balance law of the internal variables. These are the volume fractions, and I add an additional balance law for a symmetric second order stress quantity Z, and its production is phi, and this ring is an objective time derivative, which I write down here in blue. And if this omega is the vorticity, it's the Jaumann derivative. Okay, I postulate here, and you have to believe me until I come to the end, that this models frictional stresses, or can model frictional stresses.
Got it.
Okay, so
Can I just stop you? Go back one slide so that everything is clear. Alpha the subscript alpha refers to species.
Yeah.
Yeah. Okay. So we're not saying fluid or solid, we're just saying any old species.
Well, for the fluid, we don't write down such an equation, but only for the solid constituent.
Why do you make that distinction?
Well, mathematically, I don't need to make the decision. I can go through with the computations, and then in the end, I have the freedom to say for the fluid it's zero, and for the solid it's not zero.
Yeah.
Okay? So, in order to be in conformity with the theory of the class of the two pictures I've shown, I have here a thermal dependence to be able to describe pyroclastic flows, density, volume fraction, velocities, deformation rates, stretchings, vorticities, and that's it. And the arrows mean ordered arrays for those components which are compressible. N minus 1 for the volume fraction, because of the saturation I cannot have n. And for all the other variables, I have all quantities, all constituents in there. So this is the class of material behavior I need. And then I go into the entropy inequality. I must satisfy this inequality for all thermodynamic processes, which means for all solutions of the field equations in which I have substituted the constitutive quantities. And there's a mathematical theorem due to Farkas and Minkowski in the 19th century, which says that this is equivalent to this variational inequality, in which you add or subtract to this inequality the scalar product of all balance laws we have multiplied with Lagrangian multipliers, which are unknown at this level, but which will be determined through computations, and the products are scalar products. If this is a vector, so this is the normal Euclidean scalar product. This is a symmetric tensor, so this is the trace of lambda times C transposed. Okay, results. They are about computations of about 110 pages in between. Okay, so we have done this for two classes of theories. One has theta dot as a constitutive variable, the other doesn't have it, and then we can prove. The Lagrangian parameter, prove or assume. There are many assumptions which are stated in our manuscript. The Lagrangian parameter lambda epsilon is a universal, say, material independent function of temperature and temperature derivative. Its equilibrium value can be identified with 1 over the Kelvin temperature. The internal energy has no density gradients dependencies and no vorticity dependencies. And I can define a Helmholtz-like free energy in which the independent variables do not involve the velocities. If theta dot is not an independent variable, lambda epsilon is the same as the classical 1 over the classical Kelvin temperature, and epsilon is only this expression. Here's the free energy formulated, and the internal part of it is simply the free energy minus this contribution. I define thermodynamic, Kurt, now you have to listen. I define a thermodynamic pressure as this rho alpha derivative of the internal free energy, of the Helmholtz free energy. The volume fraction dependence defined this way, I define as configuration pressures. These are determined by beta. I define the saturation pressure as that Lagrangian parameter with a negative sign, which cannot be determined, which is the constraint variable. And I define the Gibbs free energies or the free enthalpies or chemical potentials as the internal Helmholtz free energy minus P alpha over rho alpha. With that, all Lagrangian parameters except the last one can be determined as functions of this lambda epsilon of the internal of the Helmholtz free energy. These quantities are expressible in terms of the Helmholtz free energy and in terms of the saturation pressure. They are all known, and the black quantities are simply diffusion velocities. Another variable pops up. This is K, and it's called extra entropy flux in these theories. It is the entropy flux plus the Lagrangian parameter of the energy equation times the heat flux plus this power of working on the diffusive motion of the peculiar stresses. The important results that are obtained is from thermodynamic equilibrium. A thermodynamic equilibrium is defined as those processes in which those variables are zero, in which the production rate densities are zero, and then you can show that the entropy production assumes a minimum of value 0. The derivatives with respect to the non-equilibrium quantities must be 0, and this Hessian matrix must be positive definite. Here I define now, and these are now the important results. This is a pressure-like variable. It consists of the configuration pressure and essentially of the saturation pressure here for the first n-1 constituents, and it is the same except for the configuration pressure for the last variable which I associate with the constraint variable. The interaction force in equilibrium can be described in this way. The first line says it's a linear combination of the gradient of the densities rho alpha of those components which are incompressible. The second line says it's a linear combination of the volume fraction gradients. And the third and fourth line give you the dependence of these interaction forces if I have chemical reactions or fragmentations in my material, and if I have frictional forces. So this is the frictional force contribution. The factors in here in the curly brackets are given and known if I know the Helmholtz free energy and if I know that vector. The stresses are also fixed. It's the pressure term which I introduced. I have elastic terms and I have these thermodynamic terms plus those terms which are due to the internal variable, and this one is the variable of the frictional stresses. I have also expressions for the entropy and for the heat flux in equilibrium, but I don't have time to discuss those. The reduced model, let's go back to solid fluid components. Both are incompressible, density preserving. I have the saturation condition satisfied. I have no fragmentation or abrasion or chemical reactions, and I look at isothermal processes. Then the constitutive equations are of the same class, I just repeat them, but the pressures I get for the solid and the fluid look like this. So I have volume fraction of the solid times this blue bracket plus a thermodynamic term from entropy, flux being different from heat flux over absolute temperature. Here I have the fluid pressure, volume fraction times something else, and this thing is the same as this thing above here, only if beta S is 0. So if I have a volume fraction dependent pressure, which means conformation pressure, then those two are not the same and pressure equilibrium is not satisfied. Okay, I can talk about this a little bit later. The stress tensor is given in this form. This is the solid pressure I just shown. Then I have elastic contributions and I have frictional contributions. I have the same here for the fluid stress, and Kurt, you can leave off this. Here you have the elastic part, but we have left off here already the frictional part in the fluid component. This is the interaction force. It's fixed once and for all. We cannot change it anymore. But there are, of course, in these expressions, you can find terms which are the divergence of something, and you are always free to throw those parts into the pressure, and then, Jim, the formulation is not satisfied. My point is you should use thermodynamics before you start doing these things which may computationally be advantageous, because the thermodynamics fixes these expressions once and for all. You are not flexible anymore. But you are in special situations able to make peace with mixtures and with a multi-phase approach. Here I want to stop. I could go any further, but all I want to say, I want to acknowledge Bob Svensson. This was done in a master thesis of Lucas Schneider, and we have worked 3 years since then, and the whole thing will come out in a book of about 200 pages, where many, many more details are shown. Here I wanted only to bring the message across. Thermodynamics is able to end long discussions because it generates fixed equations. They are there. The mathematics is the medium that tells you whether something is right and wrong. And you have very clear, if you make assumptions, the assumptions are objective statements, not personal statements like, my feeling tells me this is roughly good or not. Okay, with this I want to close.
Take a question.
Question. So, I happen to know two theories. One is by Donald Drew, and for mixtures, and the other one is by Biot. What do these people do wrong?
I don't say they do something wrong.
Now, what Biot also is very careful with thermodynamics, etc. But I've never come in his work. There is no configurational pressure.
Yeah, well, this thermodynamics brings in configurational pressure because you say up at the very beginning, volume fraction is a variable beyond the true density. And if the volume fraction is a variable, it has to enter thermodynamic equilibrium statements.
But that's what Drew does. Drew introduces the volume fraction, but he doesn't say anything about thermodynamics. So, not that I've read. But Biot does, and he's very careful with thermodynamics, but it comes out slightly different.
You can derive a theory without making the assumption that volume fraction is a independent constitutive variable. And then the configuration pressure doesn't enter. But then those people, the geotechnicians, will immediately object to this and say, our frictional stresses in hypoplasticity, for instance, involve volume fractions. They don't use the volume fraction, they use a different variable. And this theory tells you that enters the Helmholtz free energy, and if you differentiate with respect to volume fraction, you are probably likely to get something of a configurational pressure.
Okay, I think we really need to move on to the next speaker, and if there are more questions.